this video, we'll be talking about the very basics of dynamic programming. Well, what is dynamic programming and what is it used for? Dynamic programming is a type of programming used to make your algorithm more efficient. It does so by storing previously generated results. It works well when there's a lot of repetition within the algorithm and when old data is reused a lot. Now we will be looking at the Fibonacci sequence. The Fibonacci sequence is a sequence of numbers that are created from the sum of its two preceding numbers. To generate this sequence, it can be done in multiple ways. However, we want to be able to compute it as efficiently as possible. Our job is to create a function that takes in an integer n and outputs the nth number in the Fibonacci sequence. For example, if we ask for the fourth number of the sequence, it should return 3. Now we will approach this with recursion. You should be familiar with recursion before starting dynamic programming. If you, however, aren't familiar with recursion, go review it now, since the recursive approach and the dynamic programming approach both require the same foundation in order to solve the problem. Now we have to find our base case and recurrence. We know that the sequence is built off the 0th and first terms, 0 and 1. Now we make our base conditions for when n is equal to 0, we return 0, and for when n is equal to 1, we return 1. And now we need to identify the recurrence. To do so, we need to look at the nature of the sequence and how it is formed. By definition, we know the sequence is formed by numbers that are the sum of its two preceding numbers, so we can write the equation for the nth term mathematically. The equation shows that the nth term is equal to the n minus 1th term plus the n minus 2 term. Now, how can we write this in terms of our function? Well, we know what our function is supposed to do. Fib of n outputs the nth term of the sequence. Now we can rewrite as fib of n is equal to fib of n minus 1 plus fib of n minus 2. This is the recurring computation, or you can say recursive call, that happens within the function. Now you have the foundation needed for implementing the function recursively. Feel free to pause the video and give it a try. Now here is the Java solution. As you can see, we have our base case here and we have our recurrence here. I was able to simplify the base case to when n is less than or equal to 1, it will return itself, since the only values 0 and 1 return 0 and 1. Now we will be introducing our first dynamic programming concept, memoization. So we implemented the function recursively. However, this is very inefficient as we have to compute our recurrence many times. Our function's time complexity is 2 to the n, which is exponential, meaning it will become very slow as n gets larger. The reason for this is that you will notice that some of these computations were already done before, yet our function still computes them. This is where we introduce our first concept of dynamic programming, called memoization. It is not to be confused with memorization. It is a technique where we store previously computed results to be more efficient when computing newer values. Now I'll be writing the pseudocode for the memoized version of the algorithm. You'll see that it's exactly the same as the recursive version, except there's a few changes. I'll start off by writing our array for memoized values. And here's our function, fib of n. And our first condition is to check if n is already been calculated. So we check if it's storing memo, and we will return the calculated value if we already done it. Now we will write our base case when n is less than or equal to 1. Our return value will equal to n. So now we will write our recurrence. So f will equal to fib of n minus 1 plus fib n minus 2. And now we will store that value at its index. So we add it to the memoized version, so next time we check this condition, we have already calculated, so we don't have to redo this computation. And finally, we return f. Feel free to pause the video to try implementing it yourself. Here is our Java implementation of the function. As you can see, I used a map to store our memoized values, and nothing else really has changed except for this new condition where we check at this index, does it already contain a value? If so, we return our calculated value. Otherwise, we add that to our map of memoized values, so we don't have to redo that computation. At the end, we return f. Now we'll be doing a comparison between the recursive and memoized methods. Also, all the solutions and problems can be found in my GitHub, which is linked in the description. Let's get started. Here we have our recursive approach. We will be finding the 10th value in the sequence. I added a variable called operations to record the amount of times our call has been computed. Let's run the program. As you can see, here is our output of value. This is the 10th value in the Fibonacci sequence. And you can also see that we made 89 calls. Here is the Memoize approach. Let's run it with the same values. As you can see, it's still outputted 55, but you notice the amount of operations is significantly less compared to the recursive version. And this is because the time complexity of the Memoize version is linear, meaning to find the nth number, you only need to make n calls. Now let's create the function without any recursive calls, because recursive calls are very memory consuming. We will do something called a bottom-up approach. As you can see, the recursion approach starts from the nth number of the sequence and works its way down to the base cases. However, we can do the reverse of that. We can start from the base cases and work our way up to the nth number. This is why it's called the bottom-up approach. To model this approach, we can use an array to store all the values of the sequence up to the nth number. Now let's name that array dp. dp at any index I will return the ith number of the sequence. For our function, it will return dp of n, which will return the nth number of the sequence. Now we approach the problem similarly to how we approach it recursively. We need to find the base cases and identify the recurrence. Since we know 0 and 1 are the base cases, we assign them to the array. dp at 0 is equal to 0, and dp at 1 is equal to 1. Since we already know the recurrence, and we know that dp at n is equal to the nth number of the sequence, which means it returns the same value as fib of n, we can now remodel this to dp at n is equal to dp at n minus 1 plus dp at n minus 2. Now we have everything we need to solve the problem. But how do we reach dp at n without using recursion? It's quite simple. We need to find all the values of the sequence before dp of n. This is where the dynamic part comes in. Since we know what dp at 0 and 1 are, we can only find dp at 2 with the recurrence. Now we have created sufficient data needed for dp at 3. Now you can see where this is going. We repeat this process until we reach dp at n. The values we are working with are consistently changing. The new values that are created from the values that are previously created. Now think about how you would implement this approach with the information we just covered. Pause the video and give it a try. Here is a Java solution. You can see that I set up my array, my base case, and my recurrence up, and I use a loop to compute my way up to the nth number. At the end, we return dp at n. After we run our program, we can see that our array contains all the values starting from the 0th index to the nth index of the Fibonacci sequence. This is very useful because we have access to all the computed values we have so far. Now let's try some multiple choice problems to test your understanding. Here's the first question. The answer is C. Both the Memoize and bottom-up approach have a time complexity of O of n. This is because they only compute each call once, since they both store their computed values. If you print out the stored values in the Memoize approach, you will see that it contains the same values of the ZP array. The answer is A. If you're familiar with recursion, you will know that making recursive calls is very memory heavy, and arrays calls are much more efficient. B is incorrect because both approaches store previously computed values the same. Great job on completing the multiple choice problems. Now you'll be attempting to implement a function for a problem. The problem is to find the factorial of the given number n. Your job is to create a function factorial of n that solves the problem with the bottom-up approach. Good luck on solving the problem, and that will be it for this video. Everything is linked down below in the description. Thank you for watching.